When I ask whether the universe is hiding something from us, I do not mean that it has intentions or that it is playing a game. I mean something much more concrete. I mean that there may be parts of reality that are physically inaccessible to us. There may be ingredients in the cosmos that we can only infer indirectly. There may be laws that we have only seen in special cases. And some of those hidden pieces are not small details. They seem to dominate the entire universe. Right now, the best evidence we have says that everything we see with our eyes and telescopes, all the stars, planets, gas, dust, and glowing nebulae, is only about 5% of the total energy content of the universe. The rest appears to be dark. About 27% behaves like some kind of invisible matter. About 68% behaves like something even stranger that we call dark energy. We did not invent these ideas because they sounded dramatic. We were forced into them by data. I want to walk through how we know that something is missing, what we think it is, how we test those ideas, and where the uncertainties still live. Along the way, I will come back to this idea of the universe hiding things, not as a metaphor for mystery in general, but as a description of the physical limits on what we can ever know. Let me start with gravity, because gravity is our main probe of the invisible. Gravity is very weak compared to other forces, but it has one special feature. It couples to all forms of energy and mass. Anything that has energy, whether it is light, matter, or something more exotic, will gravitate. It will curve space-time. That curvature tells matter how to move. So even if something does not shine, if it has energy, gravity can betray its presence. The first strong hints of dark matter came from galaxies. In the early 20th century, astronomers assumed that stars in a galaxy orbit the center in a way similar to planets around the sun. Close in, where most of the mass is, you orbit fast. Far out, where there is less mass inside your orbit, you slow down. This is what Newtonian gravity predicts if most of the mass is where the light is. In the 1970s, Vera Rubin and others measured how fast stars and gas clouds orbit in spiral galaxies, not just near the center, but far out into the dim outer regions. They expected to see the orbital speeds drop with distance. Instead, the rotation curves flattened. The outer regions were moving as fast as the inner regions, sometimes faster. The simplest interpretation was that there is much more mass than what we see in stars and gas. This mass extends well beyond the visible disk, forming what we now call a dark matter halo. This was not just one galaxy, it was many galaxies. Different sizes, different types. The pattern repeated. The visible matter alone could not produce the observed orbital speeds without the galaxies flying apart. Something else had to be providing extra gravity. We saw similar hints in galaxy clusters. In the 1930s, Fritz Zwicky measured the speeds of galaxies moving inside the Coma cluster. They were moving so fast that the cluster should have dispersed if only the visible galaxies were holding it together. He called the missing mass Dunkel Materie, dark matter. At the time, the data were rough and the idea did not catch on widely. But later X-ray observations showed that galaxy clusters contain huge amounts of hot gas. That gas is held in by gravity. The depth of the gravitational well again implied much more mass than the visible galaxies and gas alone. Then gravitational lensing came in. According to general relativity, mass curves space-time, and light follows the curvature. So a massive object between us and a distant galaxy can bend the light from that background galaxy. This can distort its apparent shape, shift its position, or even create multiple images. By measuring the amount of distortion statistically across many background galaxies, we can map the total mass in the foreground, regardless of whether it shines. When we do this for clusters of galaxies, we see that the lensing mass is much higher than the luminous mass. In some famous systems, like the Bullet cluster, we can even see the normal matter and the gravitational mass separate. The bullet cluster is actually a collision between two galaxy clusters. During the collision, the hot gas from each cluster interacts, slows down, and lags behind. The galaxies, which are mostly empty space, pass through with little interaction. When we map the mass with gravitational lensing, the peaks of the gravitational field line up with the galaxies, not with the gas, even though the gas contains most of the normal matter. This suggests that most of the mass is in some collisionless component that does not interact strongly with itself or with gas, except through gravity. That is a strong visual argument for dark matter. We also see the fingerprints of dark matter in the large-scale structure of the universe. After the Big Bang, the universe was very hot and nearly uniform, but not perfectly. There were tiny density fluctuations. Regions slightly denser than average had slightly stronger gravity. Over time, those regions pulled in more matter and grew into the cosmic web of galaxies and clusters we see today. The details of that growth depend on what the universe is made of. If all the matter were normal, baryonic matter, which interacts with light, then in the early universe it would have been tightly coupled to radiation. Pressure from radiation would resist the growth of small-scale structures. We can simulate this with computers. We find that with only normal matter, we do not get the observed pattern of galaxies and clusters. Structures form too late and on the wrong scales. If we add a new component that does not interact with light, that is already clumping before atoms form, we get a much better match. In our best models, about 5 times more dark matter than normal matter gives a universe that statistically resembles the one we observe. A web of filaments, clusters, and voids, with galaxies embedded in dark matter halos. The cosmic microwave background, or CMB, gives another independent line of evidence. The CMB is the afterglow of the hot early universe, released about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral atoms. Before that, photons scattered off free electrons and could not travel far. After recombination, photons decoupled and have been streaming freely through space ever since. We see them today as microwave radiation with a temperature of about 2.7 Kelvin. The CMB is not perfectly uniform. It has tiny temperature fluctuations at the level of 1 part in 100,000. These fluctuations encode information about the density, composition, and geometry of the early universe. Experiments like COBE, WMAP, and Planck have measured these patterns with high precision. When we fit the data with models of the universe that include normal matter, and dark energy, we get a consistent set of parameters. The ratio of the heights of the acoustic peaks in the CMB power spectrum is very sensitive to the amounts of normal and dark matter. The best fit says that about 5% of the energy density is normal matter, about 27% is dark matter, and the rest is dark energy. So dark matter is not an ad hoc patch for one anomaly. It appears in galaxy rotation curves, in galaxy cluster dynamics, in gravitational lensing maps, in the growth of structure, and in the CMB. Different data sets, different epochs, different physical processes all point to the same conclusion. There is more gravitating matter than what we can see. That is why the majority of cosmologists accept dark matter as a real component of the universe. Now, what is it? Here we hit the hidden wall. We know how it behaves gravitationally, but we have not detected it directly in the lab. The leading idea is that dark matter is made of some new kind of particle or particles that interact very weakly with normal matter and with themselves. Candidates include WIMPs, weakly interacting massive particles, axions, sterile neutrinos, and others. Each has different mass ranges and interaction properties. We have built large underground detectors to look for rare collisions between dark matter particles and atomic nuclei. We have looked for signals from dark matter particles annihilating or decaying into standard particles. we have tried to produce dark matter in particle accelerators like the Large Hadron Collider. So far, we have not seen a clear, repeatable signal. That does not mean dark matter does not exist. It means that if it is a particle, it is either lighter, heavier, or more weakly interacting than many of our initial expectations. This opens another possibility. Maybe what we are calling dark matter is not a new substance, but a sign that our theory of gravity is incomplete on large scales. There are modified gravity theories like MOND, modified Newtonian dynamics, and extensions within relativistic frameworks that try to explain galaxy rotation curves and other phenomena without invoking dark matter. Some of them fit certain galaxy-scale data quite well, but they often struggle to match the full range of observations, especially the CMB and the bullet cluster-type systems with a single consistent model. At present, particle dark matter within general relativity gives a better global fit, but we cannot yet claim a complete understanding. Gravity itself might still be hiding something. If dark matter is one hidden ingredient, dark energy is another. And it is even stranger. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. The discovery of this acceleration was a surprise. In the late 1990s, two independent teams studied distant Type Ia supernovae. These supernovae act as standardizable candles. Their peak brightness is tightly related to how their light curves evolve in time. By measuring how bright they appear and how their spectra are redshifted, we can estimate their distances and how fast the universe was expanding when their light was emitted. If the universe were filled only with matter and radiation, gravity would slow the expansion over time. The more mass, the stronger the deceleration. So distant supernovae, which we see as they were billions of years ago, should show evidence of a faster expansion in the past and a slower expansion today. The teams expected to measure the rate of deceleration. Instead, they found that distant supernovae were dimmer than expected. That implied that they were farther away than they would be in a decelerating universe. The simplest interpretation was that the expansion had been slower in the past and is faster now. In other words, the expansion is accelerating. To explain this within general relativity, we need a component of the universe with negative pressure. In Einstein's equations, pressure also gravitates. Normal matter and radiation have positive pressure or negligible pressure. They make gravity attractive. But a component with sufficiently negative pressure can produce a repulsive effect on cosmic scales, driving accelerated expansion. The simplest form of dark energy is a cosmological constant, often denoted by the Greek letter lambda. It corresponds to a constant energy density of empty space itself, vacuum energy. In the equations, it acts as a uniform term that does not dilute as the universe expands. Matter and radiation become less dense as space grows, but the cosmological constant stays the same per unit volume. Eventually, it dominates. A universe with matter, dark matter, and a cosmological constant fits the supernova data quite well. It also fits the CMB and large-scale structure data with a consistent set of parameters. This model is called lambda CDM, lambda for dark energy as a cosmological constant, and CDM for cold dark matter. But here again, there is a hidden issue. If dark energy is vacuum energy, we can try to estimate it from quantum field theory. In quantum theory, even empty space is not truly empty. Fields fluctuate. Virtual particles appear and disappear. These fluctuations contribute to the energy of the vacuum. When we calculate this, we get a value that is many orders of magnitude larger than the observed dark energy density. Depending on how you count, the discrepancy is around 120 orders of magnitude. This is sometimes called the worst theoretical prediction in physics. It means that our understanding of vacuum energy and gravity together is incomplete. There are other models of dark energy. Some treat it as a dynamic field that changes slowly over time, sometimes called quintessence. Others modify general relativity on large scales instead of adding a new energy component. Observationally, we test these ideas by measuring how the expansion rate changes with time and how structures grow under gravity. If dark energy is a cosmological constant, its equation of state parameter W, defined as pressure divided by energy density, is exactly -1. If it is something else, W might differ from -1 or vary with time. Current data are consistent with W equals 9 to 1 within a few percent. So the cosmological constant remains the simplest fit, but the theoretical puzzle remains open. Now, how do we know the universe is expanding in the first place? This goes back to redshift. When we look at distant galaxies, their spectra are shifted toward longer, redder wavelengths. Edwin Hubble and others found that the redshift of a galaxy is roughly proportional to its distance from us. The farther away, the faster it appears to be receding. This is not because galaxies are moving through space away from us like bullets from a central explosion. It is because space itself is expanding. The distances between galaxies that are not gravitationally bound increase over time. In general relativity, we describe this with a scale factor, AT, which tells us how distances between comoving points change with cosmic time. The Hubble parameter HT is the rate of change of the scale factor divided by the scale factor itself. Today, we measure h0, the current value, with different methods. One uses the CMB and fits a cosmological model. Another uses distance ladders with supernovae and other standard candles. Interestingly, these methods give slightly different values, leading to what is called the Hubble tension. This might be a hint of new physics, or it might be unresolved systematics in the data. Either way, it is another place where the universe might be hiding something subtle from us. The expansion of the universe, combined with its composition, determines its fate. In a simple matter-only universe, there are three broad possibilities. If the density is low, gravity is too weak to stop the expansion, and the universe expands forever, slowing down but never reversing. If the density is exactly at a critical value, the universe expands forever, with the expansion rate approaching 0. If the density is higher than critical, gravity eventually halts the expansion and reverses it, leading to a recollapse, sometimes called a big crunch. Dark energy changes this picture. In a universe dominated by a positive cosmological constant, the expansion does not slow to a stop. It accelerates. Over time, regions that are not gravitationally bound to us recede faster and faster. Eventually, their light can never reach us. They cross what is called a cosmic event horizon. Beyond that horizon, events are forever causally disconnected from us. They are not just far away. They are unreachable, even in principle, no matter how long we wait. This is one literal sense in which the universe hides things. There are galaxies today whose light is reaching us, but there are also regions of space beyond our current observable universe. As time goes on, more and more galaxies will cross our event horizon. In the far future, an observer in our galaxy, or what remains of it, will see only a small island of matter surrounded by darkness. The evidence for the Big Bang, the CMB, the large-scale structure, will fade out of view. Cosmology itself will become harder to reconstruct from observation. Within our current horizon, we already face limits. Light travels at a finite speed. The age of the universe is finite, about 13.8 billion years. Because of expansion, the radius of the observable universe is larger than 13.8 billion light-years. It is about 46 billion light-years. Beyond that, there may be more of the same cosmic web or something different, but we cannot see it yet. And some of it we will never see if dark energy continues to drive accelerated expansion. We also have limits at small scales and high energies. We do not yet have a complete theory of quantum gravity, a framework that consistently combines general relativity and quantum mechanics. At very high densities, such as near the singularities predicted by classical general relativity, our equations break down. The very early universe, before about 10 to 43 seconds after the Big Bang, the Planck time, is beyond our current theories. We have models like inflation, which propose a period of very rapid expansion driven by a high-energy field, to explain why the universe is so uniform and flat on large scales, and why the CMB fluctuations have the pattern they do. Inflation is consistent with many observations, but we do not yet know what the inflating field is, or how to connect it to known particle physics. And we cannot look directly back to those times with light because the universe was opaque. We have to infer indirectly through imprints on the CMB and the distribution of matter. So is the universe hiding something from us? In a strict sense, yes. There are regions of space-time that are causally disconnected from us. There are epochs we can never observe directly. There are scales of energy we may never reach in experiments. There are components like dark matter and dark energy that we have only detected through their gravitational effects. But within those constraints, we can still learn a lot, and we have. Our current cosmological model, lambda CDM with general relativity, explains a wide range of phenomena with a small set of parameters. It matches the CMB power spectrum, the baryon acoustic oscillation scale in galaxy surveys, the abundance of light elements from Big Bang nucleosynthesis, the large-scale distribution of galaxies in the supernova data. That is a strong sign that we are capturing key features of the universe correctly. At the same time, there are tensions and open questions. We do not know the particle identity of dark matter. We do not understand the origin or smallness of dark energy. We do not have a tested theory of quantum gravity. We have anomalies, like the Hubble tension, and some discrepancies in the small-scale structure of dark matter halos compared to certain simulations. Each of these could be a statistical fluctuation, a systematic error, or a sign of new physics. One way to think about this is that the universe is not so much hiding things from us as it is revealing them gradually through indirect clues. Gravity, light, and space-time structure are our main messengers. We read them as best we can with telescopes, detectors, and theory. We know that our picture is incomplete, but we also know that it is not random. The missing pieces must fit into the existing constraints. There is one more layer to the question of hiddenness that is important in cosmology. Some theories suggest that what we call our universe might be one region in a larger multiverse, produced by eternal inflation or other mechanisms. In many of these models, regions beyond our observable universe can have different physical conditions, maybe even different effective laws or constants. If that is true, then most of the multiverse is fundamentally unobservable to us. We could only infer its existence indirectly through statistical arguments or specific signatures imprinted in our observable patch. At present, we do not have clear, widely accepted observational evidence for a multiverse. It remains a speculative extension, not part of the established cosmological model, but it illustrates how far the idea of hidden regions can go. As I look at the state of cosmology today, I see a balance between confidence and humility. We are confident that the universe is expanding, that it began in a hot, dense state. That structure grew from small initial fluctuations shaped by gravity, that dark matter and dark energy dominate the energy budget, and that general relativity works extremely well on many scales. We are humble about what those dark components actually are, about how gravity behaves at the quantum level, and about whether our current tensions in data are statistical noise, experimental systematics, or cracks in the standard model of cosmology. So when I ask, what if the universe is hiding something from us? The most scientifically meaningful version of that question is very specific. Is there a new field, a new particle, or a new aspect of time that we have not yet detected, but that will reveal itself as we push our observations and experiments further? Or is the main structure of our current model correct, and we are mostly refining details. That is not a question I can answer yet. It is an open problem. And in modern cosmology, it is one of the most active frontiers. Is dark energy exactly a cosmological constant, or does it evolve with time in a way that would signal new physics beyond our current theory of gravity and spacetime?